All right, globular clusters. Hi everyone, I'm Maddie, an ANU PhD student, and I will be talking to you about the chemical abundances in globular clusters using the GALAH survey. So I like to think about globular clusters and like this, globulars are to the universe what fossils are to our Earth. People are usually captivated by dinosaurs, they come in a variety of shapes and sizes. They transport you back to a time when the world was very different from it is now. Similarly, with globular clusters, they can transport us back 12 billion years in time. They take a screenshot of the early universe. And if that hasn't sold you on globular clusters yet, I've compiled a list of the different themes of this conference to try and convince you that you should love globular clusters just as much as I love them. Despite being thousands of more times more metal rich than the first stars, sorry Thomas, they are the oldest thing that you can reliably age, and we use them as test beds for calibrating and testing our GALAH chemical abundances. They're some of the first surviving structures of our early universe, and I've seen in some papers that they've been suggested to be responsible for reionizing the universe. Queries out on that one. Come to me if you have any opinions. Genesis, I'm still waiting for your high resolution simulations to actually be high resolution enough to simulate globular clusters, Matt. And we know that they contribute to the buildup of galaxies, they trace the galaxy's dynamical state, and then we can use to reconstruct the assembly history of galaxies. Why GALAH? Why now? Well, GALAH measures a wide range of elements all across the periodic table, as we've seen. We've got lithium, and Ella will be using 3D non-local thermodynamical equilibrium lithium abundances, got that one out, for our globular clusters, which will be amazing. And we'll be using C and O to test theories of what can happen as you go up the red giant branch. What I'm most excited about, though, is the slow neutron capture elements. So within the helium burning shells of giant asymptotic giant branch stars and potentially some other stars, heavy elements are slowly bombarded with neutrons and decay into many of the elements we have here. And finally, we've got the rapid neutron capture elements, or element, which occurs in more energetic phenomena where there's access to a large number of neutrons in a very relatively short time frame, hence rapid. Why now? GALAH's been around for a while. Why are we just doing a globular cluster paper now? Well, these are keel diagrams using currently available DR3 data for two clusters, 47 Tuc and Omega Centauri. On the x-axis, we've got our effective temperature, how hot our star is. So going from left to right, your star is getting colder. And on the y-axis, we've got our gravity. So as you go up, you have less and less gravity in the star. And now if I show our new DR4 abundances, or stellar parameters, I should say, we have a much tighter red giant branch for both clusters. And the colors are based on metallicity, which is iron, not oxygen. Iron is how we measure metallicity. We can see that DR4, at least in Omega Centauri, we can start to actually pick out the metallicity difference as you go from one side of the red giant branch to the other. And from these improvements with the pipeline that we've done, well, Sven's done, I can't take any credit for it, it's all Sven, we can now probe the chemical abundances of globular clusters with GALAH. So I want to take a quick detour and tell you about the next big thing in reality TV. I'll get there. I'm assuming most of you have heard about The Bachelor, right? Yeah. But have you heard of the globulars? It's the next hit TV show where we look through all of the GALAH abundances and you can decide on what your favorite globular cluster is. These are our contestants for season 1 of the globulars. NGC 1851, a lovely cluster, 11 billion years old and lives in the constellation Columbus. Or we have the elusive E3, who's a little bit older, only 12.8 billion years, and can be found hanging out in the constellation Chameleon. And so these are the keel diagrams, so back to science, of our 10 clusters, ordered by the number of well-measured stars in each cluster. The color bar is centered on the average iron abundance within the cluster, so any colors that you see within these points mean that we have iron abundance variations in these clusters. I'd like to point out as well that M4 is Maddie Powell's data, and she's kindly letting us use it for the study, but definitely go check out her paper on M4. And this is a work in progress, of course. We're actively trying to get more well-measured stars, particularly for some of our smaller clusters. Now, the sodium-oxygen anti-correlation, we've heard about this a bit already. If you publish a globular cluster paper, you are legally obliged to include a sodium-oxygen anti-correlation. Again, piggybacking off Maddie's talk and some of what Thomas was saying, the anti-correlation is the result of multiple stellar populations within the cluster. Stars that are oxygen-rich and sodium-poor are part of this first generation, and stars that are sodium-rich and oxygen-poor, yes, are part of the second generation. But if you now color this by barium abundances, so that's our S process element, we can maybe report the tentative result that barium deficient stars are members of the first generation of stars in Omega Centauri, which is exactly what we'd expect given our knowledge of the theoretical modeling. If you want me to extrapolate this, please ask questions at the end. But this is really good news and is something that can't be done in other surveys such as Apogee. So based on these GALAH results and our understanding of globular clusters, since we've had this high resolution spectroscopy, I'd like to outline a new approach to star cluster classification. To our extragalactic astronomers, this is the view that you would probably see. We've got open clusters, globular clusters, and then dwarf galaxies and sometimes ultra-compact dwarf galaxies. Now, to Milky Way astronomers, we'll go into a little bit more detail. What's known as type 1 and type 2 globular clusters. Not very informative names, but type 1 clusters are essentially, when you look at its photometry, you see two populations of stars. And type 2 clusters are where you see multiple populations of stars. But to a stellar spectroscopist, this is not enough, and I think we can do a little bit better with our naming scheme. So type 1 clusters, these will be the true globular clusters, things that have a bimodal population based on our light element abundances, and an ion abundance spread and an S process spread of less than 0.05 dex. These are kind of loosely based on the values given in Coretta et al. 2009. And of course, the poster child for the true globular cluster is my favorite cluster, 47 Tuc. On the other end of the scale, we've got our nuclear star clusters, and then we've got Numea et al. For 2020 for a review on the nuclear star clusters. But to a stellar spectroscopist, a nuclear star cluster is something that has anomalous ion and or S process spreads above that 0.05 dex level. And it's reminiscent of a dwarf galaxy almost. Or they can be physically tagged to a galaxy itself, either surviving or accreted. And of course, Omega Centauri. It's not a globular cluster, it's a nuclear star cluster. Please tell everyone. The third and kind of last component that we want to break globular clusters up into is a metal complex cluster. These are clusters, again, with anomalous ion and or S process spreads above the 0.05 dex level, but it does not necessarily imply that they came from an accretion event. And this is to alleviate the problem where we have too many weird clusters based on how many accretion events we have in the Milky Way. They're just two things don't add up. So things that would go in this category, NGC 1851, NGC 362, and GALAH is really what's going to help us decide which cluster belongs in what category here. So to summarize, we've got some upcoming GALAH papers. Of course, Sven's leading GALAH DR4. We want to present a paper on the new framework for these star clusters and present some data verification, those kind of boring things, making sure that our abundances are exactly what we think they are and they're consistent with the literature. Then we'll do the fun stuff of the light element abundance patterns. And Sarah's also leading a paper on looking for nitrogen-enhanced stars and hopefully disrupted globular clusters. We've got an AAT proposal, so anyone who's on the ATAC, please give me time. And we want to expand the number of clusters that we have here to equal or surpass the number of clusters in Apogee. Apogee has 32, we have 10. I know we can do better. And finally, additional science cases that can come with this. We can do chemodynamical analysis of accretion events based on the globular cluster populations. We can search for extra-tidal stars and we can verify different photometric abundances. But if you have your own science topic and you think that you can kind of tell us more about what globular clusters are doing, come and talk to me. We need better steps forward in what to do with these things. So I finish on, ask not what globular clusters can do for you, ask what you can do for globular clusters.